Alright, so we're integrating. I'm not going to do the actual integration, but the setup is important. We're doing an upside paraboloid, and we're integrating that function x squared plus y squared, but again, I'm not going to do that. I'm just going to go through the setup of how to set up an integral. The spherical is not going to really work because one of the main conversions is that rho squared is equal to x squared plus y squared plus z squared. That's coming from the equation of a sphere, and the radius is rho. That would be your equation of that sphere. So that's one of your main conversions, and you don't have z squared. So even if you move things to one side, you're going to have z plus x squared plus y squared is equal to a squared. You do not have the appropriate conversion because it's not a sphere, it's a paraboloid. So that's not going to be the way to go. It's going to be, I want to say, nearly impossible to try to get through that in spherical. I mean, it's probably possible, but it's going to be a super ugly grind. Way worse than even doing rectangular. So anyway, you want to definitely do cylindrical. So one thing you want to note is the paraboloid, you want to look at the side view sometimes, depending on how you're going to integrate. You want to look at the bird's eye view of the xy plane. And if we are going to do cylindrical, this immediately converts to z is equal to a squared minus r squared. Okay. Which, I'm trying to think, well, okay. Oh, that's good. You could convert it to, let me see, r squared is equal to a squared minus z. I'm just seeing if I can solve for r. I don't think I want to be doing that. So I like this. This is workable, so I think I'm going to leave it in that form. But if I do that, I gotta think now. It's going to be plus or minus 2. Oh, it's going to be ugly. Yeah, I don't want to do that for sure. Anyway, I do need to know probably, I'm just going to go ahead and do it anyway. It's a good habit to just, I'm going to need to know where this intersects the xy plane. Which, by the way, since we're going to switch it to cylindrical, that xy plane is going to be like the r axis essentially, because your r is just going to be some distance out there, and that'll represent that distance out there, r away from the z axis. So this would be r, this would be z side view, and then bird's eye view, it would be xy, but the r and theta, the usual way for polar. Okay, so let's start working this out. Intersection is important. And what you would do is note that this is z is equal to 0 right here. Your xy plane has the equation z is equal to 0. That's this plane right here. You want to find out where it intersects that. So I guess I'll do it here. Intersection of z is equal to 0 and z is equal to a squared minus r squared. You get z by itself, and each of these, so you can set it equal to each other. 0 has to be equal to a squared minus r squared. R is equal to plus or minus a, but with r for polar or cylindrical, you usually disregard the negative. So r is equal to a, meaning it's going to be a circle of radius a, which means it's hitting a there, and I mean, it's not negative a, it's still a, because a is just a radius going out. Alright, anyway, I don't even label it because it's going to be confusing. Alright, that's going to be relevant to whichever way we decide to do it, I think. But it's definitely going to be relevant to me trying to do it. I'm trying to think, can I do it with R first? Because he did I saw the cone, he did it. The cone was different. The cone side view. When I think the cone was z, basically it's going to be like z is equal to r or 2r or some constant r. So you have it clean. On this one, the r is squared and the z is not, makes it a little bit trickier, but with the cone in the side view, they're just lines, and so you can solve it for r in terms of z or vice versa. So the cone itself is very convenient and gave you a little more options. I don't think working with R and doing it with R first is going to work. So I think the only reasonable way I can think of right now is doing Z first. I'll talk about. Oof. Oh, I did say we can omit the negative for the same reason over there, but I still feel like I'll go back and set it up with respect to R. I'm gonna do the easy one first, the one that I feel is intuitive, which is to do Z. It is very common to want to just do Z first, then R and theta. R and theta are interchangeable, but usually that's kind of a very common, most common order to do it in. You still have a Jacobian for cylindrical, which is the same Jacobian as for polar, which is just an extra R there. Your integrand, I'm not going to put it, but your function, I believe, was x squared plus y squared, and you would want to convert that to cylindrical coordinates. And again, this is designed to convert to a nice R squared. So your integrand is going to be R squared. But the main thing is setting up your limits of integration. So again, I'm going to do Z first. So here I'm working with Z first. That means whatever's in here, Z is your variable. You are going to treat R and theta as constants as you work in here. And that means going to your picture and visualizing it, you want R and theta to be constants. So you pick a random R and a random theta, which means I'm just going to pick a random R and a random theta right there. So like right here, an R that and a theta that, whatever angle that is, and that's my point right there. Right there. And now with that, I'm going to go along Z. So parallel to the Z axis, I'm going to do a slice right there. I'm going to hit the paraboloid there. I'm going to make a little slice or a little straw hole there. It's going to come out the other end. That's fine. But anyway, that's the slice that I'm going to do. And that's what I need to do right here. Z is equal to Z is equal to, for my first variable Z, with R and theta just being that arbitrary constant for that slice. And now I need to think about my upper curve. My upper curve is a paraboloid, and I need it in terms of Z is equal to, and I already solved it earlier. So up top it's a squared minus r squared. Then it slices through the paraboloid and then comes out the bottom, and the bottom is the Z is equal to 0 plane. So Z is equal to 0. And that's your Z's. Now, what you need to think is, you got to get all those slices. So looking at the bird's eye view is relevant here. I need to basically do all those different straw slices to do the whole thing, basically. So now, those two limits of integration, the R and the theta, just needs to be whatever I would do if I'm trying to integrate over this footprint or the base of that paraboloid, that little paperweight looking thing. Okay, and then so from there, so I'm done figuring out my Z's. I'm going to be going from 0, the xy plane, to the paraboloid. My integrand is going to be r cubed, the r squared from my function, and the Jacobian r, and that's my Z, and I'm done with that layer. And that right there represents this one slice for a particular r and a particular theta, and now I'm going to try and get all the r's and thetas for this particular thing to get all my slices covering the whole thing. Anyway, how am I doing this? It's just a circle of radius a, so I'll probably do r next, and that's a simple matter of what r's am I trying to do. I'm trying to do all my r's from 0 out to a. So that curve is r is equal to a. So next is my r goes from 0, my inner curve, to my outer curve, r is equal to a. Next, I want to integrate with respect to theta last. And I just want to make sure I get all of this for the full circle. If it's a quarter circle, I'm only doing 0 to pi over 2. If it's half circle, 0 to pi. But here I want to go from 0. And I want to integrate all of those slices all the way around to get the full circle. So that means my theta is going from 0 to 2 pi. And that's it. That's your setup. Z first, just a random point in your bird's eye view, a random theta and r, and do a straw slice cutting right through there. Upper curve to lower curve, and then just make sure you integrate over the entire shadow or footprint of that region. For, if you recall the football, I think I mentioned it, but the football, you'd have to look at like the shadow. So the shadow would be cast by the biggest radius. And so if you did it in a similar way, you'd have to integrate over that fattest radius, the waist of that football, and look like that. And you have to figure out what that is. How wide is the radius at that point for the football one? Anyway, you integrate that. That should be your answer. Let me backtrack and let me try and force it with a different order. Even if it doesn't work out, it'll be illustrative of, you know, how you would try to force it, or how you would go about it that way. And it's still useful to like actually go through it, even if you decide it's not the best way and it's going to be too ugly. So let us talk about that. Okay, so the other one, he did have situations where he wanted to do R first, then maybe Z, then maybe theta or something. My integrand's still the same. I still have the same Jacobians because it's still a conversion to cylindrical coordinates. The order that I do those cylindrical coordinates in is irrelevant of my Jacobian or the integrand. But it'll make a difference in my boundaries. So now I'm going to do R boundaries. Which means I'm going to treat Z and theta as constants, which means what I should do in my picture is pick a random Z. I'm going to pick it right there. No, I'm going to go a little bit lower, sorry. Pick a random Z right there. And a random theta, which means in my, let me show my bird's eye view again. So a random Z, some height, and some random theta, which would just be just a random angle that I'm just coming out of. So I'm going to come out that way, which means I'm coming sort of out that way, like that, but up here. So I'm going to do a slice that way. It's coming out from the center axis, shooting out, just like that. If I drew it over here, it'd be like right here. That's my random Z, and it'd just be popping out that way. Oops. Slicing that way at some random theta direction. All right, so my inner radius is obviously 0. My outer radius, so going from inner to outer, my outer is coming when it hits a paraboloid. So right there, inner and outer, right there. So I need that equation, and I did it earlier in terms of R. I need it in terms of R, the same paraboloid, but in terms of R. That's going to be R is equal to the square root of a squared minus Z. Is that right? Did I solve that correctly? A squared minus Z, yeah, square root. Okay, so that would be it. Okay. So that's my first layer, doing that little piece, that little, I don't know, like pencil coming out of the thing. Anyway, then I need to make sure I do it for the entire solid. So next, what do I want to do? Okay. And here it's different options. I'm going to do theta first. Yeah. But these are interchangeable. Either way is not that bad. If it's going to be difficult, it's going to be difficult here, which might not be that bad. I'm looking at it now, and I thought it was going to be ugly, but I think it's workable. I'm gonna write it out in both ways, but I'm not doing it here. I'm just doing the video to show you the setup. Okay, theta. So looking at this slice, I need to do all the thetas. So I'm going to start here, theta is equal to 0, and go all the way around at that same Z height though, and I'll get this cross section that way, like that. So that'll be theta goes from 0 to 2 pi all the way around the circle, and that gives me that slice there now. Then I want to do all my slices, starting from, next I want to do Z, and I want to figure out what Z ranges to. And my last bounds of integration should always be constants to get the whole thing. So I'm going from Z down here all the way to Z up there. So 0, 2, and I didn't figure out what that is, but if I plug in x, that's a squared. A squared, yeah, because x is 0, y is 0. Yeah, a squared. And that's it. a squared minus z. Sorry, I wrote it wrong here. A squared minus z, right? Okay. A squared minus z. Sorry, fix that. A squared minus z strictly. R is equal to 0. R cubed dr. If I chose to start with r but then do z then theta, let me just mention how that would work. I would do my r again, going from 0 to the paraboloid at picking some random z and some random theta, coming out like that. That's my slice. And then if I chose to do z next, I would still want to do all those. Alright, let me change this and make it more obvious what's happening. It's coming out that way, coming right at us, coming out at that angle. Okay, and if I did all the z's, I need to be taking that slice and doing all the z's starting from there all the way there. So I'll get that sideways slice. All the z's starting at 0 to still a squared. But once I do that, that's the slice I'm doing, a vertical slice. And then I want to add up all the vertical slices to make the whole region. So then I would do that slice, that slice, that slice, and add up all the way around, going that way, all the way around. So then I would go 0 to 2 pi. And computationally, it'd be almost the same because theta and z are not in your integrand, so it doesn't affect it. But that's how you would do it with r first, which, again, I think it's doable. I was looking at that and thinking that's not going to be really easy to work with. But when we do the antiderivative of r cubed, it's going to be r to the 4th. Plug that in, it'll be, the square root would be gone, and then I think it's workable from there. Anyway, that's your setup. I don't have space and to make errors, so I don't want to do it on the board, but I'll work it out on my iPad and then send you the actual thing of one of these and the other way, and we should get the same answer. So anyway, but that's the setup. That's how you approach it. Make sure you're drawing pictures and doing slices, which are where you're going. Remember, when I did z first, I'm slicing along the z-axis, parallel to the z-axis, at a random theta and z. If I'm doing r first, I'm going out r from inner to outer. All right.